Okay, now let's implement the ADA UGNN. Firstly, let's review the equations in this paper and see what parts we need to implement them. The equation 2022, the 22 defines the loss function, and all we need to do is to find an appropriate vector matrix F to make this loss function to minimize it. And in this equation, there are two vector matrices we need to imply. The first is the S, the clean signal. And in the real world settings, I think that the clean signal S can be obtained by the each node's one-hot encoding of each node according to their labels. That means that, for example, in the Cora, S can be obtained as the number of nodes times number of categories, and F is the filtered signal. We can use the MLP to transform the original signal F into the filtered signal. That means that MLP firstly transfers the original F to n times D and n times H1, A times H2, then n times the number of category. So let's implement this process in our coding. Firstly, we need to import some necessary module, and then freeze the random seed to ensure the replication ability. And also here we import our datasets. Here I use the Cora, and later I will generate the script to other datasets. The Cora dataset has the following attributions: X age index, Y label, tree mask, validation mask, and test mask. Then we use the GPU to accelerate our train loop. Here we can get the original signal F by graph.x and the label of each node graph.y. So the clean signal S can be obtained by to convert the label of each node to their one-hot encoding. So S is like this one. And here we can construct the graph information. We use the network X. Firstly, add the nodes into the graph and add edges. Then we can obtain the adjacent matrix A and the degree matrix D. Then we need to define some useful variables which we will use in later. Zeroth vector, A height, the square root of the degree matrix, and the normalized degree matrix. Here we can define our MLP. I use the 3 layers, so I define the W1, W2, and W3, then initialize them. Also, we need to check whether they are leaf nodes, because we need their gradients in the train loop. And here we can train our model. Firstly, we need to convert or transform the original signal F to the filtered signal F, like this operation. And then the first term, in the loss function can be obtained by doing this. Firstly, make a power operation and then sum them. This measures the filtered signal F and with the clean signal S. And then for the second term, this one, the ADA UGNN defined in the equation 23. We need to calculate the central node Vi of their differences between their and their neighbors, Vg. But we can implement this by using for loop, but it will cost much time. Then I use the matrix format to accelerate this process. Firstly, I generalize a vector like this one. This is h1, h1 to h1, h2, h2 to h2, and hn to hn. There are n number of each of them. And then the second vector is the h1, h2 to hn, and h1, h2 to hn, h1, h2 to hn. There are n of them also. Then we make a subtract operation between these two vectors, so we can obtain vi with all other nodes, with all nodes in the graph. That means that h1 minus h1, h1 minus h2, and h1 minus h3. The shape of it is the n times n and d. Later we measure the distance between vi with all nodes in the graph. That means that firstly power them and then sum along the second dimension, and review this and reshape this format into the n times n. So like in this operation, we get the difference between the node vi with all other nodes vg, and then we can filter the differences according to the adjacent matrix. That's to say, if node vi connected to node vg, that means that the aij is greater than 0. We preserve the difference. Otherwise, we set the difference into 0. So we can get the difference between vi and its neighbors vg. And also summarize the and the total loss is the first term plus the second term. Then we make the backward operation and update these parameters. Then define the test function. So we can see this model's performance. Here I set the epoch to 1000, and every 100 epochs test this model. This is very fast because the in the forward in the training function there are all the matrix operator, no without the for loop. So we use just only 20 seconds and iterate 1000 times. The final accuracy rate is like around the 22%. We save this model. This is the simplified UGNN. Also, we need to consider the local smoothness. Like in the papers 20, this term CI, this term, each node have their local smoothness. Also, this paper defined CI in the equations 30. Here, the H2 is H2 is a channel-wide operation. Like the mean of them, or the summarize of them, or the max of them, and then aggregate the neighbor information to a vector. And the H1 is a single layer neural network to convert the neighbor information into a scala. And then the sigmoid, there is a sigmoid function to get this to impute the scala into the 0 to 1, and the upper and the skew parameter s to control the upper bound of the CI. So we can implement the local smoothness C in this code. Firstly, we also need to use the repeat function to generate a h prime to help us to get the local smoothness. And then, like the difference here, we also need to filter the h prime and the h prime. If vi connected to vg, we preserve their channel-wide information, or otherwise set them into 0. and then summarize measure the distance between Vi and Vj. And this line is the implementation of the equation 30. Here we obtain the local smoothness C, and make a broadcast to add the local smoothness. And the other operation is identical to the first script, so we can run this script. Okay, we iterate the model also 1,000 times, and the accurate is the 85%. This is to consider the local smoothness. We have some improvement, and here I implement this by just the semi-supervised instead of the train the whole data sets. And this is and other operation is also the same as this one. And this script I generalize this model to other data sets. Let's say here I make a configuration file. Here we can design the dataset which to use, CiteSeer or Cora or Smoothness. The random seed and the upper bound and learning rate X logging steps, these parameter and hyperparameters. This I pushed it into the GitHub. You can check it on the GitHub. Thank you.